The 6.3 alternative examples, this is question number 2. In many games involving dice, rolling doubles is a desirable thing. Rolling doubles means the outcome of two dice are the same, such as 1 and 1, or 5 and 5. And the probability of rolling doubles when rolling two dice is 1 out of 6. If x represents the number of doubles in 4 rolls of two dice, then x is binomial, with the number of trials being 4, the probability of success on each trial being 1/6. We know that the rolls are independent of each other, and the probability of success stays the same at 1/6, as well as it being a binary situation. You either get doubles or you don't get doubles. So we're going to go over what this means here. What is the probability of x equaling 0? And what is x? X is the number of doubles in 4 rolls. So we're saying what's the probability of not getting any doubles in 4 rolls of dice? When you read the problem, you should recognize that and this is true for all binomial distributions and kind of binomial situations. This is going to be a big tree diagram kind of problem. And so what we're going to do here is I'm going to show you what the tree diagram would be for 4 rolls of the dice. So here we're going for doubles, kind of like in Monopoly when you're trying to get out of jail. N equals 4 because we're going to roll 4 times, and the probability of success is 1/6. X is going to represent the number of doubles. And so what could happen? We could either get no doubles, 1 double, 2, 3, or even 4 out of 4 doubles. And if you look at this, here's the first roll. We could either get doubles or not get doubles. That's 1/6 probability to get doubles, and then the complement is 5/6. Given the fact that you just rolled doubles here, what's the probability of rolling doubles? Well, the events are independent, so 1/6, 5/6, and so on. If you were to follow down these 4 rolls, we have different kinds of outcomes. And so the first outcome that we have here is doubles, 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 doubles. That's right down this tree path. The next tree path is doubles, 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 not doubles, right here. In that case, we got 3 doubles. In this case, we had 4 doubles. That's what X is keeping track of, is how many doubles were rolled in those trials. Another possibility, doubles, doubles, not doubles. So that's why I wrote D, D, and D, and so on. So this is a full picture of all 4 rolls and what could happen when we're concerned with the number of doubles showing up. And in part 1a, it says, what's the probability that you don't roll doubles at all? So what branch of the tree is that? That's going to be no, 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 no. That's this one down here. 0 doubles is no, 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 no. All right? So how are we going to do part A? Well, when we go down the tree diagram, as we did in chapter 5, we're going to be multiplying 5/6 times 5/6 times 5/6 times 5/6. Another way to think about that is 5/6 to the 4th. And when you do that on your calculator, you get that it happens about 48.2253% of the time, which is a lot. Even though it's only one branch of our tree, 48% is going to end up being the highest likely thing to happen when you roll these 4 dice. It's very typical to not get any doubles. Now, in part B, it says, what's the probability of x equaling 1? What's the probability of getting exactly 1 doubles? Not getting doubles twice, not getting no doubles, but getting doubles once. So looking back at the tree diagram, what does it mean to get doubles once? Well, over here, here's a once. Getting doubles, then no, no, no. So doubles, no, no, no. I think I showed this on another video here. So getting doubles, no, no, no. So that's doubles, no, no, no. Another way to do it, though, is not getting doubles, then no, no. And I showed that here. So there's another branch. And down here is another branch, and down here is another branch. So it looks as though in part A it was pretty simple because it was just one branch. But if we start doing getting 1 doubles or getting 2 sets of doubles or 3 sets, now we're dealing with lots of branches down this tree. And I know we're only doing 4 rolls of the dice, but when we get up to like 20 rolls or 30 rolls of the dice, it gets very complicated. So we've introduced a formula that's going to help us solve all the cases. Now I know in part A, we just were able to do this by hand, but I do want to show you the tools we're going to use for the much harder problems coming up. Anytime that a problem asks you to find exactly 0 doubles or exactly 1, whenever you see an equals here, we're going to be using binomial PDF, the probability density function. Okay? And n equals 4 trials, p is 1/6, and in this case, when x equals 0, we're talking about 0 doubles. So from the formula sheet From the AP formula sheet, this is where we see binomial distribution with parameters n and p, and this is the formula for finding x equals however number of successes we're looking at. So, in the case of this problem, the first part of the formula right here is n choose k. This part here essentially tells us the number of branches that are in our tree diagram. The next part is the number of successes, and the last part here is the number of failures or not having successes. So what does that look like in the example up here that we did? Well, the example then would be probability of x being 0, 0 doubles, 0 successes is 4 choose 0. Notice this is not a fraction. This does not mean 4 divided by 0. This is 4 choose 0, and that might be a new symbol to you. This part is the number of successes, 1 out of 6. There's 0 times of getting doubles. And then there are 4 times of getting not doubles. That's 5/6. When you do 4 choose 0, there is a way to do it on your calculator. I'll explain it once, but we won't be using it much more after that. To do this on a calculator by hand is you hit the 4 first, then you hit math, go over to the probability menu, hit option 3, then you hit 0. On your calculator, you'll get 4, n choose r 0, and then that'll give you 1. It essentially tells you that there's only one branch where we get no, 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 no doubles. And putting it all together, we get the same answer we got before, but using the cool formula. Also, there is a fast way in your calculator to do this. Hit second, VARS, variables. That'll take you to the distribution menu, and you do binomial PDF. Careful, because there's a PDF and a CDF. Then you'll be prompted to say how many trials, n equals 4. What's the probability of success, 1/6. And the x value means how many doubles are we concerned with? In this case, it's 0. You write on your paper x equals 0 equals binomial PDF is 4, 1, 6, 0, and you get the same answer. So what happens now when we're looking at getting 1 doubles in part B? Well, in that case, let's look at the formula here. I told you in the beginning that this part tells us the number of branches. And to get 1 doubles, there are 1, 2, 3, 4 branches that are involved here. And if you were to do 4 choose 1, it would give you the answer 4. That's how many combinations there are. And then when it comes to the next part of the formula, I told you this is the number of successes. Well, let's look at this. Success, failure, failure, failure. That's why it's 1/6 to the 1 and 5/6 to the 3. And so if you throw all this together, the probability of getting this case, this case, this case, this case, all put together is 4 of these branches, 4 of these products. So you should have 4 times 1/6 to the first times 5/6 to the fourth gives us 38.58% of the time we are expected to throw doubles exactly once when we roll the dice 4 times. On our calculator, we type in binomial PDF, 4, 1/6, and 1, and you get the same answer.